Today we're talking about exoplanets. So let's go ahead and move on, I guess, to the next slide.
Yeah, Guido's reminding me it was Kepler. uh, Hang on.
The little telescope that could. I love that. All right. So, of course, the very first thing we need to talk about, of course, is going to be what happens if you have a system with an exoplanet. And so, I guess we can go ahead and stroll on over to this website. And you guys have already seen this before. So, I'm not going to spend too much time on it. And so, for this very first site that we're going to be showing here, we're kind of given a sense. I mean, this isn't a true sense of what an exoplanet system would look like, but close enough. Where in this situation, we have a single star, and orbiting around that single star, we have our exoplanet. Now, the key thing I want to note here is if you guys are able to see the upper left-hand corner, this corresponds to the location of where we can set the parameters for our, in this case, exoplanet system. And so right now, the mass of the planet is about 100 times less than the mass of the star. Now, in any real exoplanet system, this is not true. Well, any system like our own, this would not be true. Just to give a few quick numbers, for example, if we were to compare the mass of Jupiter to the mass of our sun, Jupiter's mass, if I'm not mistaken, is about 1,000 times less than the mass of our sun. Our sun being a G-type star, and so this particular exoplanet system that we're kind of trying to simulate here has a situation where the mass of the planet is 100 times less than the star. And I don't know if you guys can see this, but if you kind of look very closely at our star, it kind of wobbles a little bit, right? I'm not too sure if you can see it, but it's represented there exactly in the right plot here. At the very bottom, it's represented by what's known as a radial velocity curve, where we're able to see the radial velocity of the star as a function of time. So the left plot at the very bottom, and this is going to now show you guys a better view of the system, but you can now better kind of see the little bit of wobble that's going on with our extrasolar star. Actually, excuse me. At the bottom of our screen, we have the radial velocity of the planet in the left plot, and at the very bottom right, we have the radial velocity of the star. And what you kind of see is that it's very little wobbles. And the reason why I'm bringing this up is that it's because of the fact that we have to have very sensitive instruments to be able to pick up these little small wobbles. But we're going to get into that with our next slide. So we're going to go ahead and move on to our next slide now that we've talked kind of about the dynamics of an exoplanet system. Of course, in this case, it's just assuming that we have a single star and a single planet. So moving on to our next slide, we have what we see here. If you guys just give me a quick second. So Larry asks, it is precessing. So the act of a planet precessing is typically I believe that's associated with its axis of rotation and how that axis of rotation moves over time. Looks like a broken game. But basically what I was getting at before was the fact that as the planet orbits the star, and really what's happening is both the planet and the star are orbiting the center of mass of the system. And because they're both orbiting the center of mass of the system, we kind of get this whole wobble effect with the star. Now, in this animation that we're showing here, the wobble effect is a lot more pronounced. And typically, the larger the wobble, this typically means that the planet itself is one, more massive, and two, close to the star itself. Of course, the closer the planet is to the star, the more the wobble will be, and the higher the mass the planet is, the higher the wobble will be. And so, in this situation, we're looking at a planet orbiting a star, orbiting a star, and we kind of see this whole situation of this kind of like bar of light at the bottom of the screen with lines in it. Well, this particular animation at the very bottom of it, that corresponds to the spectrum that we're getting from the star. Now note, you can only get a spectrum from a light source. So in one of our previous streams, we end up showing a binary star system where we were able to see essentially two spectra. Each spectrum coming from its associated star. But in this case, because we only have one star, we only have one spectrum. And so this is actually a very good indicator. This is actually a very good indicator, indicating that it's only, of course, that there's an object that's orbiting the star, and it's massive enough and close enough to be able to produce, well, massive enough to be able to produce noticeable changes in the spectrum of the star. And of course, you can see in the plot here, this plot showing the radial velocity of the star over time. And what's happening to the light itself, of course, it's undergoing a change from being either blue shifted to being red shifted, depending on whether it's moving towards us or away from us. And so, with that said, I believe this is probably the most common way in which exoplanets are observed, actually, by means of looking at the blue shifting and red shifting of light of the star, due to the fact that it has a planet orbiting it. Not anymore with Kepler. Good point, Black Hole Chaser. So this kind of brings us up. This actually that was actually a good segue. This actually brings us to our next slide. And so, of another means of being able to examine these exoplanet systems, and that's through the power of photometry. So Joe was actually talking about this earlier. This was what you were talking about, right, Joe?
Yeah, this is actually the software that I'm writing, the transient tracker project I'm working on, is actually we're performing photometry on star fields. So this is
cool.
This is very useful stuff for me.
Okay. Well, what we're looking at here, guys, essentially is, well, of course, we have a big orange or reddish orange circle representing our star, and in time we kind of see this kind of little black dot kind of go across the upper portion of the top of the disk of our star here. And so what this is supposed to represent, of course, is an exoplanet, in our case, transiting the star. Now, a key thing that I did not mention with both of these techniques is the plane of the orbit is important. With the spectroscopy case, the wobble, of course, or the plane of the orbit of the star, of the planet, around the star, must be such that it's edge on. So that means that we're able to actually see the wobble of the star because of the fact that the system is edge on relative to us. And in this situation, for us to be able to see a planet transiting, again, the system has to be, for the most part, the orbit has to be such that the planet at some point crosses somewhere between us and light coming from the star. And so what we can do now. So yes, DPI. Geometry is important. The plane of the orbit is important relative to us. Yes. And so drawing our attention now to the bottom of our animation here. As you're looking at the animation of the planet transiting the star, you're kind of seeing this whole situation where there's going to be a dip in what's known as a light curve. And so along the y-axis, we're looking at the change in luminosity over the luminosity of the star in cases where there's no change, of course, versus time. And so the key thing I want to draw our attention to is the range along the y-axis. If you notice, these changes in the amount of change in the light is extremely small. I mean, if you look at this, it's a max about what is that, 2% change in light. And so you need very sensitive instruments to be able to detect these changes in light. Sensitive instruments such as, like, for example, as someone already mentioned, Kepler. And so this is also another means of being able to detect exoplanets. And then when I was in graduate school, these two types of ways of detection was what I was taught. Now this third type is actually is kind of relatively new to me. Learned it not too long ago, actually. And so we're going to go ahead and move on to our next slide here. So what we get here is our third and last technique of detecting exoplanets, which is microlensing. And so the picture here is that, of course, we have some star that we're looking at off in the distance, and at some point in time, some random point in time, we have a planet or a star and its exoplanet pass between our vision of the background star. And so what ends up happening is that as the planet and the and its host star passes between us and that background star, it causes the background star's light to undergo a magnification. And the general trend of that magnification, or that light that we're receiving from the star, will follow this red curve that we see at the very top of the of this image. But not just that, the physical the physical picture that we're going to end up getting of the star will look like what's represented by what's known as these lensed images. And so this particular technique is another means of being able to detect exoplanets around extrastellar stars. But the issue is that it's one, random, and more than likely once it happens once, it's never going to happen again. Or at least it's not going to happen within one's lifetime, more than likely. And so lastly, and this is clearly a very short conversation on exoplanets, we're going to go ahead and move on to our very last slide. And we're going to go ahead and have some fun with some data. So we're going to go ahead and go to this webpage, exoplanets.org. And here, Joe and I have already set up a plot using some exoplanet data. Now, if I'm not mistaken, this data is from the Kepler mission, as well as, I actually have to re-verify this, but I'm pretty sure that it's using Kepler data. Or maybe it's just using it's using other data sets. So at the very upper right-hand portion of the web page, we have data sets there, and it's using the Orbit database and other data sets. And I don't exactly know what other data sets are, but we're not using Kepler. I guess we could click Kepler and see how that changes the plot. Probably not by much, but if you guys look at the y and the x-axis, and along the y-axis we're showing orbital period in units of days in this case, and essentially orbital separation between the exoplanet and its host star along the x-axis. And I'm going to leave this question to you guys, the audience, to tell me, what physical law are we displaying here within this plot? Now, I would ask Joe, but Joe and I have kind of already discussed it, so I'm not gonna.
And Joe doesn't remember anyway, so.
Larry, you said that image of exoplanets in the Andromeda galaxy. Will that microlensing or so microlensing is the technique that's used to be able to determine as a means of being able to determine if a star has an exoplanet. But I'm not too sure of exactly what you mean by that image of exoplanets in the Andromeda galaxy. I don't recall us showing. If you're talking about the initial slide, the title slide, this is just the animation I grabbed, I believe, off of Wikipedia. I don't believe I actually showed an image. And also with that, with what you just said, I'm not too sure if we've actually detected exoplanets in other galaxies. I was always under the understanding that many of the exoplanets we've been able to detect are within our galaxy. So Black Hole Chaser is on to it. And he's giving you guys a hint, guys. Okay, yep, what Larry said. You guys got it. Kepler's third law. Oh wait, you guys. Well, you got the guy's name right. Kepler's law, and it's Kepler's third law, that relates the orbital period of an exo or a planet to its host star. And so basically, what we're showing here is that Kepler's law holds for systems outside of our own. That's right. That's right, Silent Storm. And so actually, I mean, the neat thing about this website is that you can actually do a lot of other, you can also establish other plots of other characteristics of exoplanets if you wanted to. I figured that this will be a very fun one to show. And I mean, to be able to indicate whether or not it's right or not, all you would need to do is measure the slope of essentially the line that you kind of get from the data points. And if I'm not mistaken, the slope should be, I think, like 2/3, or it should be like a fraction, like 2/3 or something like that. Because the law states that the orbital period squared is proportional to the orbital separation cubed. So. But yeah, guys, we're kind of starting off nice and easy with our return here, talking about exoplanets. But you know what? Even though Joe and I said we were probably going to bring it up, I'm going to say a big thanks to Joe right now, because if you guys can remember with our previous streams, my computer was having all sorts of problems with being able to host the stream, and Joe's kind of taken over that part of our show, and he's doing a perfect job right now. So thanks Joe.
No problem. I'm trying to get that YouTube video to load onto the browser that we have up, but I'm having a kind of a hard time. Let's see here.
Oh, nice. Black Hole Chaser has it's given us a
Copy link
YouTube
location.
that, because I don't know if that's a. Oh, that is so really that's really cool, Black Hole Chaser. I'm looking at the video myself on my computer.
That's calculus right there. That's everything moving at all times.
Yeah, that kind of like slightly kind of it looks kind of like a slinky. It's kind of been squeezed. At least that's the thought that's coming to my head right now. I got kids and they love slinky, so. So wow. I'm noticing that we've only went about like 30 minutes today. Probably even less than that. Um
Pamela only went about 15. We put in twice the work she did.
well guys, we're opening it up. We're opening up of course the chat for, like questions and stuff like that. But yeah, today's stream was pretty short. So
Let's see what OBS says we've been going. 25 minutes.
okay, it's not bad at all actually. So I'm trying to go through some of the comments here. So what Black Hole Chaser said is correct. You're right. You're seeing the stars orbital wobble around the center of mass of the system, which is caused by the planets. Right. And like I said before, I mean, you guys are, of course, always make sure that I'm saying things correctly here. But I think the spectroscopy is by far the number one means of being able to determine exoplanets. But photometry is also very important. But I think the numbers are such that many more exoplanets have been determined by spectroscopy versus photometry. I'm not too sure, but I think that that's the case. Yes, DPI is correct. Most methods favor one, larger exoplanets, and two, close exoplanets. So you want large exoplanets and you want them to be close to their host star.
Jupiter's for real.
Yep, hot Jupiters. Well, Joe, do you have anything to add to our conversation today about exoplanets?
No, I don't think so. Like I say, I'm currently working on photometry with the Transient Tracker project. I am probably within a couple of weeks of releasing a new alpha version that just anybody can download and install an BigJay and play around with telescope images. I even have where to get good telescope images to play with it in the README stuff. So I'll drop a link to the repository if anybody wants to go look, but I should have had this ready and don't. Oh, GitHub was down earlier. I hope it's back up. Give me a second here. GitHub never went down when it wasn't Microsoft that owned it. I'm just kidding. Well, it didn't that I know of, that's true, but let's see here. I finally have the link and can post in chat if you all are interested in the software we're writing. Of course, a lot of people know about the CosmoQuest website already, but not a lot of people know about these projects that aren't on CosmoQuest yet, and my Transient Tracker project is one of those. So go check that bad boy out. It's I didn't realize I had it on the screen, but it's fine that I did. I'll get it to that. Right here is the usage that tells you how to install BigJay and then install the plugin, and down here under useful information is where you can go and grab like NASA telescope images. Well, they're more than NASA, but NASA hosts them all, and then there's some directions on which specific images, the 32-bit FITS images, that the plugin works. And you can literally grab all these star clusters that I've been testing my algorithm on, and I've also since then been provided with some simulations by Dr. Plazas. I'm sure you all have seen him stream from time to time. He's helping us with a podcast in Espanol and a lot of other cool shit. I mean, stuff. See, Moohoodles? See? Told you. We're all grown. There's not many kids, and if they're not hearing the S word, they're fine. But this stuff slips, and we just really try to...
Guys, again, you can imagine this is just a conversation amongst friends. We're all friends here, so it's cool.
But anyway, go check that site out, and then I'd say, well, we're ideally going to be taking this Alpha 2.0 functionality with us to AGU in December, right?
Yep.
So we're working on. You're going to be there, I think, right? We're going to have another DC hangout sesh. It sounds like.
That's right.
Nice. We just got to get the old crew back together. We got to get Sandla and Maya. Let's see. I guess James won't be with us since he's moved on, but it's going to be a lot of fun. I'm already excited about it.
He'll be there in spirit.
Yeah, but that's all I got.
All right. Well, guys, we loved today's conversation with you guys. We look forward to our conversation with you guys. Yeah, AGU, the American Geophysical Union. They host a conference. I think it's annually. It happens once a year. And of course, if you go ahead and do a search for AGU 2018 meeting, you'll be able to find out some of the information involved with it. But both BigJay and I will be presenting some information at the meeting this year in Washington, D.C., and I believe it's in December.
Yeah,
So,
it's mid-December. It's like about 10 days before Christmas.
yeah, this is actually both of our first time going to this, and exactly what Black Hole Chaser is saying. I hear like it's like the number of people that are going to be present is like insane. So, and like Joe just said, I keep getting like having to go back and forth between BigJay and Joe. So I'm just gonna say Joe because that's what I'm used to. But yeah, but Joe's gonna be presenting his transient tracker software at the meeting, and I'm going to be talking about the incidence angle analysis work that I've been doing, and I've talked about during past streams. So yeah, we look forward to it. But yeah, guys, we will be back again this upcoming Friday after another episode of Daily Space. We look forward to it, and we will see you guys then, guys.
Have a good one, friends.
Bye.
Thanks for hanging out.